That's pretty much all you got to know, to be honest. Yeah, we got more to do in 5 minutes. Is there anything else from homework?
Actually, can you go over 4.3, number 21?
Yeah. So this one, is it currently an R base or another base?
Another.
Good, it's another base. So this should be an easy one because it's not blank spaces, right?
Yeah.
So help me out. What are the spaces that these are in?
1, 16, 32.
Nope.
Is it 16 times 6?
Yep.
36.
Never
No,
mind.
wait.
I thought it was
720.
Okay.
You got a very low probability of guessing.
256.
There you go. And then one more.
4,097.
And what does C mean? C means passing. No.
Something I find out.
A is 10, because that's the first 2-digit thing that we have to convert to 1 digit. 11 is B. 12 is C. Good. So this is actually 12 of these. And then 6 of those, 7 of those, 9. So now you just put in the calculator 12 times this plus 6 times that. Yeah, it's going to be a big ass number. Big old thing. So higher bases take really big numbers and make them more compact. Because every place can hold more in it. That makes sense. Lower bases will take our little number and make them big. Right? Base 2 is like, oh crap.
Number 45 on 4.3.
Oh yeah. Yeah. So I don't know if you noticed on the page before they explain it, right? Do you see that? Okay. So it's base 5. And they say that these symbols, this is 0, this is 1, I guess it's based on clock, sort of, 2, 3, and 4. I like it. So again, base 5, just kind of gives it away, but how many symbols do I need for single digits? We're in base 10, right? How many single digits do we need? What do I go up to? What's the number that I go up to? 9. All right, so that's why they go up to 4, because it's base 5. Cool. All right, did that have anything to do with the question? No, I don't care. It's explaining what's going on here, why this makes sense. And then they say, all right, they tell you what these symbols mean. They tell you you're in base 5. So you know the places. What would the places look like? 1s? 5s? 25? You keep multiplying by 5, right? You're not adding 5, or else that would have been 6 from 1. You multiply by 5, multiply by 5. Just like we multiply by 10 for our system. And so forth and so on. So they tell you, what is this? So they only have 2 places for number 45. And say, what's this dude here? Yeah. So just like when we were doing Babylonian, the first thing I would do is take their symbols and make them into my symbols, and then I do the math. So what actually is in the 5's place? What is this? 4. 4. So there's 4 5s and 3 1s. Stay with me. Jeff is better than Tylenol P. What's up?
So then isn't it like 20 plus 3 times 20?
Totally. Yeah, it's that easy. It's that simple. The math is not very difficult. Even when you use freaky ass symbols that we're not used to. We're just not used to. In fact, you don't have to get used to these. They only work for this one problem.
Yeah.
Right? But you could actually do something like this for your own number system if you want. I mean, that's why I kind of assigned this problem. And the other one with the colors, just to kind of give you guys some ideas maybe for your own number system. So by the way, nothing's due today. I just try to set today to be the day you should kind of have an idea. And I told somebody else, if you want to run some stuff by me, because somebody was too worried, they kind of understood that this project is really huge in scope. There's a lot of flexibility. So if you come see me with some ideas, I can rein you in. I can say that won't work, but this will make that work. I can help you kind of structure it. If that makes any sense at all. So I mean, it's insane. You have no idea, and I don't blame you, about how much flexibility there is in this. I already told you can use colors, you can use frequencies of sound, you can use stuff I haven't even thought of. So it's almost too much. So if you have some ideas, I can help you kind of refine it a little bit before you have to get in little groups and explain it to other people, right? Yeah. Anything else from homework before we get back into where we left off? Let's see if this dude's webcam up yet. All right, here we go. This is actually something that was done back in 2007. I was searching to find some decent pictures to show you related to Fibonacci. And I found this article about some research somebody had done. Let's see what's the quickest way I can get there. I'll tell you what, before I show you that, somebody left their mailbox open, that's good. Let's see if it's me. So I don't know if anybody's trying this out yet. We're down to Google. Let me show you this. I talked a little bit about Fibonacci trees. Like if you look at trees, a tree that's grown up and hasn't had disease, hasn't had limbs cut off. Let me show you some quick images. I remember when I first learned this, when I went jogging around my neighborhood, I had to stop at a tree and go, holy shit. But here's a decent picture if you guys can't see that. There. But if a tree is kind of grown normal, then as you go up, it might branch off into 2, and then it branch off into 3, and then branch off into 5. And it's just sort of the way it works. And it's weird, but it sort of makes sense from one perspective that nature builds on itself as things grow. That's one way to look at it. But here's what I just recently discovered. Let me log in. There I am. I sent myself the link. I love when I email myself, I just say here. This is kind of amazing. So it's just back in 2007. So it's a little technical, but basically these people were trying to construct. Have you guys you've heard of like nanobots and stuff like that? Right, nanostructures even, where you can build things atom by atom. Have you heard of that? That's some cool shit.
That takes fucking forever.
I know. Well, thankfully they weren't building bridges or anything, but they're just building very small things. It didn't take a long time. And just as a proof of concept, they laid out like a comic strip or something in atoms, using atoms. So you have to use an electron scanning microscope just to see the comic. It was kind of nifty. But very quickly, let me see if I can get to the point. So some people, this is back in 2007, like I said, they were trying to create these microstructures, 12 micrometers across, right? So micrometer, ooh yeah. We're going to talk a little bit today about metric systems, so we'll talk about that. And the structures they built, if they made them into shapes of cones, there were these stress patterns that were based on Fibonacci. So remember we talked a little bit about, I got to remember to turn you around. We talked a little bit about the ratios of sides. I didn't really get into it very far, but basically, let me start with this. Let me try to build my way to there. And this is on page, if you want to kind of go along in the book. Where does it start off? Bottom page 279, but let me actually just jump to the rectangle. It's more interesting. Use the same things. A. So if you construct this so that this length to this length, that ratio, this length to that length, is the same as, what would it be, Jeff? A to B, it should be, right? Yay, Jeff. If you construct a rectangle so that this length divided by that length is the same as that length divided by this length. Let me stop there for a second.
Is that in thirds evenly?
No, it's not.
Okay.
In fact, if it were in thirds, then this ratio would come out to be something different. If you construct it so that that's true, this ratio comes out to be that number we kept getting when we divided parts of the Fibonacci sequence. Remember we did that the other day? 1, 1, 2, 3. We went far enough, and when we divided them, it came out to be about this. Do you guys remember that? Happened Monday. And the technical form of this, because that's not exactly what it was it? It kind of went forever. So in reality, it looks like this. So that's what it really, if you did that in your calculator, it would come out to be 1.618, blah, 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 blah. All right, okay. I like it so far, so good. Maybe. So there's a lot of math that went into, obviously there has to be some math to go into going from this approximation to that very exact answer. But still, if you do set that up, that's what it would come out to be. And this is related to when they did the studies and they constructed shapes that had something going on in this part and they had something else going on in that part, that was more aesthetically pleasing than if I cut it in the middle or cut it at some other place. They've done these studies, right? And it kind of makes sense because we're attracted to things that are healthy. Biologically, we just are. And there are signs that things are healthy, and one of the signs that things are healthy are they're growing correctly. And when things grow correctly, they have Fibonacci sequence all over the damn place. Just because it kind of models how things grow. If you don't grow right, if you have disease or something happens to you, you're not going to have those ratios. You're not going to look as pleasing to somebody because you look like you've been not healthy. You guys kind of follow me.
I don't get that formula at all. How that?
Well, all right. I don't know if I want to get totally into this, but if you construct this to be true, this ratio will come out to be this. How else can I say this? There's a lot of math in between, but if you work some stuff out, you end up, this is getting a little bit overly mathy, more than I wanted to, but you get to this thing, this is, and now, does anybody remember how to solve that? Just to kind of throw some algebra in?
Basically the plus or minus.
Yeah, quadratic thing that some crazy people have songs about. That's crazy. We started off negative b plus or minus.
The square root of
4
square
b squared minus 4ac over a squared 2a.
Close enough. All right, cool. I like it. All right. I've taught that so much, I'm going to be C now, so I'm going to be able. Negative b plus. Who's that? So if you throw in all the stuff you get there. Now there's a lot of math that went from here to there, but I don't want to focus too much on that. So this is just an introduction to this. You can get deeper into any part of this, or you can just accept the surface and go on. It's totally up to you how much deeper you want to get into anything we talk about. I'm just hoping something we talk about is interesting to you. At the very least, if you go to Google and just type in Fibonacci plants or something, just type Fibonacci whatever the hell, and just see what it comes up. What really gets cool, stay with me now, this is where things get really cool. If you, let me ask you this. Do you guys remember this kind of thing? Let me see, do this real quick. 3, 4, 5, is that cool? Yeah. Little right triangle. So let me ask you this. If I blew that triangle up, and this was 6 and this was 8, what would that be? 10, right? Is that cool? So those are similar triangles. 3 is to 4 as 6 is to 8. The proportion you can set. Does that ring a bell?
Sure.
Do you see how that's sort of the same thing?
Yeah.
This rectangle is similar to this one. It's the same rectangle, just turned and shrunk. Is that cool? I mean, that actually is cool, as I understood. Maybe a little bit? All right, so here's what's really stupid cool. If that triangle, good job, if that rectangle can be cut so that this rectangle exists, and this rectangle is the same as this one, just smaller, I could do the whole thing again. Right? Let me orient it the same way. So it doesn't really matter, but let me draw the line the same way the book does. So I can draw a line just like I did here. Just imagine this thing flipped over like that. It's the same rectangle. I'm going to draw that line so that that's true again for its sides, and then I can do it again. Again, let me draw it in the same kind of place. So now watch, this is kind of cool. This is remarkable. This is awesome. This is nifty. How are we doing so far?
That's where the spiral.
Yeah, dude. So if you connect the corners, In the same kind of way, you end up, and of course it's going to get smaller, smaller, smaller. It's going to get in there. You get this, what's called a Fibonacci Spiral. All right, even if you didn't catch everything, you can step back from this picture and see how that's created. I think it's in the book too. Yeah, page 280.
It's right there on
Isn't
the
that a
page.
seashell?
Yeah, it's right there. I like it. So there's what I'm trying to draw. And anytime I draw, I basically have to say trying. But this is nice. This is exactly what's going on here, right? See that? Is that cool? Now, so they created these. This is so awesome. Especially, I'm sorry, I'm really excited because I didn't even know this. They created these little structures. And they noticed that if they made them into cones, stress fractures would happen. There were stresses on this poor little structure, dude. It was stressed out. And the stress showed up in the form of Fibonacci spirals. It's not easy to see here, but basically if you follow, that's a Fibonacci spiral. They did the slope of it, they could tell it was a Fibonacci spiral kind of thing starting to happen. Blah, blah, blah. They found the stress was concentrated in regions following a Fibonacci spiral. So one reason they think that this might occur in nature, why this might be how things grow, is it's related to stress minimization. They're trying to minimize the stress, and so the way you grow and develop, if you grow according to the Fibonacci sequence, that ratio, you'll reduce the stresses on you. That's neat. I haven't even looked into this beyond that, and now I'm like, show me the freaking article. I want to see this. It's so cool to finally have like a real reason for this. And this is 2007. I'm like, how much more have they done with this? Have they verified this? All right. There you go. Thank you for going through that with me. So let's come back to focusing more on this. So this leads to this. Doing that more and more with every single rectangle I make leads to this spiral. And they often do this. If you look on page 280, they incorrectly related to this. Well, I don't trust you. Just read them. If you don't have the book too bad. They relate this to the shell of a chambered nautilus. Chambered nautilus is this little thing with a shell that swims through the ocean. Chambered nautilus. And its shell kind of looks like that, but it's not exactly Fibonacci. It's actually called a logarithmic spiral, which is very close to Fibonacci, but it isn't the same. So we can't claim that. In fact, they do call it a logarithmic spiral in here, but they still set it right next to the Fibonacci spiral. A little misleading. Okay. And for some reason, again, if you have the book, every edition chooses this horrific picture when they talk about the aesthetics of art. This picture has some major problems. I don't like it. Right? They try to point out that the line that they drew in the picture is right where it should be. And I'm thinking, that's not saving that picture for me. I'm sorry. Right? They could pick a better picture to show this. Page 281. Invitation to the sideshow. La Parade de Cirque. And they also talk a little bit more about the music stuff in there. Any musicians in here? Anybody, if I said, and I'm not a musician, so I actually have to look it up, a major sixth. If I said a major sixth, anybody know what that means? Nobody that
So no.
far. Dude, and it's major. Apparently, a major sixth consists of the note C, and the note C vibrates, it's a C, Jeff, there you go, at 264 hertz. And hertz just means times per second, right? And an A vibrates at 440, so A at 440. Somebody help me out with a calculator. What's 440 divided by 264? Take a guess.
1.618.
Dude, almost. I think it is. Who is it?
1.6 repeated.
So pretty sweet, pretty close. 1.6 repeating, right? So it's pretty close to 1.618. So that's a very pleasing tone. If you play those together, the major six is a very pleasing tone. If you play two that did not have a ratio close to that, it would sound, it'd be like me playing. It would be horrible. Oh shit. So that's not close to Fibonacci. Again, this is all nifty. It's almost somebody was just bored and said, well, 1 plus 1 is 2, and 1 plus 2 is 3, and that's interesting. And then it leads to all this connections with all these things. To me, it's really amazing. Okay.
Do you know of any literature that, I mean, it seems more accessible to poetry, but anything that mimics Fibonacci? Any, like,
You mean literature?
Yeah.
Like, oh, you mean like forms of literature? Like a haiku kind of format.
Yeah.
Not off the top of my head, but we might as well Google it, right? Google exists. So let's see, Fibonacci.
What about this?
Let's just do Fibonacci poetry. Of course, it's probably going to be poetry about Fibonacci. Oh, here we go. Perfect. First thing. A fib. That's funny. Fib is a multiple-line verse based on the Fibonacci sequence so that the number of syllables in each line equals the total number of syllables in the preceding two lines. I like it. So it's like a Fibonacci-like. What is a fib? So there's one syllable, two syllables. So now the next one has to have three syllables, a poem. The next one's got to have five syllables. Mathematical. All right. That's interesting.
That's not.
It's not really.
Pleasing at all.
It's. I know. And why not? So I'd rather be interested in trying to search for like natural occurrences of the Fibonacci sequence. See how that was like forced? That's forced. And then, so it's not going to necessarily have any beautiful aspect to it, right? But if you find something where people have studied certain cadences and they say, oh, look, the Fibonacci sequence shows up, maybe they have a sound that's pleasing. That's the kind of thing you want to look for. So many, when you search for Fibonacci, if you see somebody made a song based on, that's crap, go away from that. You want to find naturally occurring Fibonacci-related stuff. That's what you want to search for. Yeah, inherent aspects of Fibonacci in something. Exactly. Okay. So maybe some of you guys will search something, and you don't have to turn any into me. I just want you to be interested in it. The homework, if I'm you, I might be a little concerned what the homework's going to look like. You, considering how you construct the sequence, some of the homework is going to be take the 7th number, add it to the 8th number, notice what happens. So there's going to be some, for example, the sum of any 10 consecutive Fibonacci numbers is always divisible by 11. Okay, so it's not earth-shaking, it's weird, right? I mean, so any 10 consecutive Fibonacci numbers you pick, I don't care what they are, how far out you go, if you add them together, it's divisible by 11. And so what a mathematician would do is go, all right, let me try to prove that. So we have to try to write it generally, try to prove it, try to see why it works, right? But for you, you just have to pick any 10 you like, any 10 consecutive ones, add them and show that it's divisible by 11. Just divide it by 11, show that it comes out to a whole number. So some of your homework is going to be like that, a little contrived, but I want you to see how much other stuff is going on with the sequence. And then some of it's going to be measure your computer screen. If you don't have a computer, measure the one in the tech ball. I want to see them come up to you. What are you doing? Give me a look. As you measure the computer screen. One semester we talked about billboards, and I was curious about billboards, and come to find out billboards aren't near the Fibonacci. And why do you think that might be?
Yeah.
But why do you think that is? What are billboards there for?
So you notice it?
So you notice them. So you're like, oh, okay. I don't know if it's going to do any good for the message on it. But it's like the alarm waking you up and getting your attention. That's the only thing I can think of is that's why they did that. I don't know. Or I have no idea why they did that. Maybe it's federal regulations or something. I don't know. But you're right. They're mostly disgusting. Right?
The Deadpool one was.
Except when I got down.
It was worth the chuckle. It wasn't like hilarious, but.
That movie was
And like piranhas, how like
The movie
3 of
was
them. Like,
good.
Uh,
I liked it.
Oh, we voted.
Well, it was certainly better than the earlier two.
Just farts or
I think the
whatever.
what?
I like when he left the doll from the earlier movie. I said, here, you can have that. Or was that in a trailer I saw or something?
No,
That was in the movie. Yeah, the doll of him
I
from
went to
the
the
X-Men.
Vista Theater. They got a bar, so I remember like.
Yeah, they got that Mulligan's thing or whatever.
The what?
In the AMC.
Yeah.
Yeah. Isn't it called Mulligan's? All right. Enough about that. The other part of your homework, so you got part that they're going to be looking at the Fibonacci sequence itself. Part of it's going to be measuring stuff and seeing how close it is to the Fibonacci ratio. We already talked about note cards, for example. You have 3 by 5, 8 by 5. Those are from the Fibonacci sequence itself. Right? It's crazy. Blah, 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 blah. Then you have some that are like, is this Fibonacci-like? So is this sequence here, is this sequence Fibonacci-like?
Yeah. Yes.
They're just taking a safe bet.
Yeah.
No.
8 plus 14 is, yeah, so it's not.
No.
So you just gotta, that's how you gotta check it. I like, I missed, You just check to see that the next one is the sum of the two before it. If it isn't, then you just say, no, it's not. Did I talk about this last time? You can have a sequence built off of 3, so like the preceding 3 terms.
Right. You didn't talk about it.
And if you do this, so it'll be 4, 5, 9, then it'll be 17. You guys see what I'm doing, right? You add the 3 to get the next one.
That would still be Fibonacci. Like
That's not Fibonacci-like. No. This is its own deal. And it starts with the letter L. I always forget the name of it. It's not the Lucas sequence. I always forget what it is. Since we're talking about sequences in general, if you type a sequence in, there's actually a whole website devoted to, where is it? OEIS. The Online Encyclopedia of Integer Sequences. Oh, yes.
Wow.
You know I would know about this. What is the name of that? No. Just the name of it. Come on, guys. They get way too into this. Screw them. They're not going to tell me. Oh, here it is. Well, duh. Fibonacci. That's just silly. Fibonacci, because it's 3. Yeah. If you do this, the ratio doesn't come out to be 1.618. It comes out to be 1.7 something or other. But it stays that. Eventually, it just gets closer and closer, 1.7 something, or its own little number. So let me see if you guys, you're all looking this direction right now. So Fibonacci is somehow dependent on side lengths of a rectangle. Is that cool? We went through that earlier. There are other sequences that are built off of other shapes, maybe a 5-sided shape, a 6-sided shape, and looking at their diagonals. So I went to a conference where this lady introduced this whole topic, and I thought, well, the golden ratio comes from this shape. You with me? And it has this sequence, not this. It's got this sequence to go with it, right? She had done all this study about finding ratios in the shapes, and I said, well, do they come from sequences? Do they have their own sequences? And she said, we don't know. I'm not sure. So I got all excited. I found several sequences, and you guys are like, yeah, good job, whatever. But I was like, yes! As a mathematician, it's very difficult to kind of find something that nobody's done yet. It's sort of like an explorer or something. Everybody's gone everywhere. Shit. Except for certain parts of the ocean. But so that was kind of nifty, that you can go beyond rectangles. You can do higher number of sided rectangles and have their own golden numbers, golden ratios.
So, like, what's the sequence of, like, a dodecagon?
I can't remember. It's like a really interesting ratio of trig functions.
Oh, gosh.
Yeah, so it all depends on the angle. So the rectangle has 90-degree angle, so it reduces to a really nice thing. So whatever shape you're looking at, the angles between the diagonal and the side are going to be different, and then you use trig functions to figure out what the ratio is. So if I did that formula to a rectangle that's shaped right, I would come out with 1.618, blah, 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 blah. If I do it to a dodecagon or whatever, then I'm going to come out with something for each of its diagonals. It's going to have a lot of diagonals, possibly, right? You guys, you don't have to understand all of what I just said. I just want to throw that at you.
What about a circle?
No, sir. A circle, sort of. Poor little circle, dude. It doesn't really have any vertices, right? So for that function to work, it's got to have these corners.
It has to have pi.
And a circle, you can either say it has no vertices or it has an infinite number of vertices. So either way, it's a little too extreme. Okay.
This is a little cooler than the other bullshit we looked at. It's a Fibonacci. No, the Fibonacci, the fibs. No, just the fibs. So it's a Fibonacci sonnet, and rather than like structuring it in this really awkward way, all it is each sentence builds on itself in the Fibonacci sequence. So it's 2 paragraphs, but they're paragraphs. They're not
So you start with some phrases and then you build off those
like
phrases?
it says pen, and then paper, steady hands. Write a word, write another word after that. Then write 2 words to make a sentence. Next, write 2 3-word sentence followed by a sentence of 5 words. So it's just, you're just lengthening. Yeah, there it is.
Oh, in 2007. 2007 was a big year for them.
Yeah, Microsoft 2007.
Fibonacci was this dude who lived in Pisa back in 1200. They had lots of rabbits. Yeah, okay.
That's it right there.
Pen, paper, steady. So one is a guy named Bruce Holland says you can use a Fibonacci to write super short 2-paragraph stories called Fibonacci
Hey,
sonnets.
what did they say?
What is this font, dude?
What did they say?
Where's some
It's
comics?
arbitrary.
Where's some comics?
This font is called. You didn't want to read this, did you? Yeah, it's neat. I like that. All right. Okay. Good. I mean, now, just to show you something really quick. If you type in Fibonacci music, you anything you type in, there's going to be these. You know that if you've ever been on the internet, there's holes you can go down that are just like holy shit. So if you type in Fibonacci music, let's see if this shows up. What was I trying to do? Fibonacci tone. Here it is. Supposedly there's a certain frequency of music, music you can do that would calm you, that has like spiritual connotations.
Oh, like the brown voice?
Sort of like the polar opposite of that, I guess. Not down here so much as up here.
But it's like, I want to be skeptical towards those things, you know, like...
No, that's what I'm saying. You
I
should
have
be.
friends that are sick of geometry and all that shit, but at some point it is